Okay, this is video number 3. On video number 2, we did confidence intervals for the mean. Those problems either gave you the mean and standard deviation from a sample, or they gave you an actual data set and then you had to type that into L1, period. Today we're doing confidence interval for the population proportion. Remember, that's back to Camp P. That's the yes-no type of questions. To show you what you might want to have out, again, you can have the notes printed or you can take notes as we go. One more reminder about this sheet. Right in here sort of summarizes what we're doing today, that these problems are not going to give you the mean and standard deviation. They're going to say something like 43 out of 150 people believe da-da-da, or 49% of 150 people believe. They'll talk in fractions or percents. Also want to remind you about the confidence interval chart. Last time for confidence intervals for the mean, we needed, well, this chart is just to help you show me the setup, right? Because we actually get the answers off of our calculator. Most of the chart is for the T values based on degrees of freedom. You know, you have the percentages of confidence across the top. You had to look up degrees of freedom. Today, you're going to see that the formula we use has a Z in it. So some of you may not be able to read that, so I want to make sure you see that very bottom row below the horizontal line. It says Z critical values. So this, just this bottom row, is where we're going to look up the values that we need to show the setup of the confidence interval today. Back to the cheat sheet. Remember last time, video number 2, we did this formula for the confidence interval for the mean. Today, we're doing this formula. And that's why you'll see there's a Z in it, as opposed to a T up here. So we have this formula. Maybe I should circle those. What I just circled are the only things that you will be looking at on the cheat sheet for test 3. The rest of the stuff is test 4. Here are our 2 confidence intervals that are on test 3. And remember, this stuff was all X bar, P hat, sampling distribution, handout 9 stuff. So what I circled will be the only spots that you look at for test 3. And the other sheet, well, 2 sheets. I handed this out before spring break. I also reloaded this in the mayhem module. These are the 2 problems we're going to be working today in the video. And then towards the end of the video, we're going to be discussing this handout. So you need to have these 2 handouts in front of you. All right, we'll assume, and have your calculator out. We'll assume everybody's organized. So I'm going to start to work through the notes that go along with the video. All right, confidence interval for the population proportion. If you remember, we had the general form of a confidence interval. It said estimate plus or minus. Well, the estimate for the population proportion would be the sample proportion, which is P hat. Then the general form said Z times standard deviation. This really is going to stay a Z. It's never going to turn into a T. Now, the standard deviation of P hat from handout 9 was this. But if we don't know what the population proportion is, how can we be using it in the formula? So we're going to have to tweak that a little bit. These are actually going to become p hats. So you can kind of tell just from looking at the formula, all you need to do is identify the p hat in the n. You'll get the z. Off of the CI chart, so you'll have everything you need for the setup. So this is going to be the last row on the CI chart. That's where you're going to get that from. When we go to our TI-83, it's going to be stats, test, 1, prop, z, int. The int is for interval. They just ran out of space for the title. Prop is for proportion. We're only doing one proportion. And then the z is referencing that there is a z in the formula. So it's very easy to memorize these shortcuts on your calculator. This shortcut can be a little bit tricky. This is a spot that some students get an error on their calculator. So when we practice these problems, you absolutely have to have your calculator out and practice along with me so you'll make sure you don't get stuck and get an error and then can't answer the question. All right, we're going to, so you can pause the video if you want. I want you to go read this first problem. I think it's called number 22. I stole this from a different textbook, but it's about ban on smoking. So this is a bit dated, but I always do this problem also just to bring in some history of banning smoking in restaurants. I don't know if y'all remember when you were young, you would go to Applebee's, people would be smoking at the bar, the families would be sitting along the outside, or at Cracker Barrel, you used to have to say smoking versus non-smoking section. It really did start on the West Coast, and then it slowly moved. Again, Virginia was probably one of the slowest to implement non-smoking in public establishments. So, a lot of the research that was done originally, I guess this is back 1998, was on bartenders. Bartenders have employment, but they were exposed to secondhand smoke the entire day, their entire shift. This comes back to, in America, we think it's important for our employees to have a safe workplace environment. It's not fair to them that they are being exposed to something that could be dangerous for them. So that's just some history of why a lot of research was done on bartenders. This is a really long problem. It looks a little overwhelming, but once you read through it, it boils down to two things. 21 of 39 sick bartenders got better. Bartenders got better after the ban. They did not measure these bartenders' lung capacity or oxygen levels or anything like that. They just basically returned a few months later and said, hey, you used to be sick. Did you get better? And then the bartenders would have said yes or no. That's why this is definitely a proportion problem. There is no mean and standard deviation. There's not a data set. And this one is giving us the information in fraction form, just so we can wrap our minds around this number, because 21 of 39 is a bit awkward. Make sure you know that your p hat is 21 divided by 39, which is 0.5385. So approximately 54% did get better. That information where it says there's more than 400 bartenders, That was just them trying to say we did good statistics. We had plenty of bartenders to get a random sample from. So we're never going to use the 400 in this problem. The problem asks for a 95% confidence interval on the true proportion. We know what happened with those 39 bartenders. We want to make a statement about all of the sick bartenders. All right, let's set up our formula. We always want to practice showing the setup. I'll come back to the Z. So p hat plus or minus, p hat 1 minus p hat. The N is 39. Bottom row, under 95%, you will see 1.96. This is actually the most famous number in statistics. You probably don't remember this, and it's okay. You don't even have to write this right now. But originally, when we were learning the Z-chart, I think it was part of the video you watched, one of the problems said what Z-scores separate the middle 95% from the extreme 5%, and we figured out that it was negative 1.96 to 1.96. This is not coincidence. This, from the Z-chart, is the foundation for confidence intervals. Remember when we talked about being 95% confident? We basically said 95% of samples, once you build the confidence interval, will include the truth. 5% won't. That's what this is relating to, that these 95% of samples, we'll call them the okay samples. And see, where's my other color? That 2.5% and that 2.5%, that 5% extreme samples, maybe they had outliers in them, whatever. Those are the 5% of samples that, when we build our confidence interval, are going to lead us astray, are going to end up with a wrong result. So it all comes back to understanding the Z-chart, the beginning of, I guess, test 2 material. But back to this. Now we have to go to our calculator. I forgot my calculator. Hold on. All right. Go to, I'll turn your calculator on. So go to Stat, move over to Test. Let's see, we're 1 prop Z int. Do not stop at 1 prop Z test. We are not doing hypothesis test. Do not stop at Z interval. That is not it either. 1 prop Z int. Hit enter. See, there's not that much there. This one is easy. When the problem gives it to you in fraction, it goes straight into the calculator. But notice, the calculator does not ask you what p hat is. It asks you for x over n. Maybe I should write that. P hat is, just by definition, how many out of the total, right? So it asks for x and n. So our x on this problem is 21. Our n is 39. C level, 95. Calculate. That is the confidence interval. This is the 95% confidence interval for the true proportion of all sick bartenders that got better. Somewhere between, 38 and 69%. The book that I stole this problem out of, while they made fantastic problems, they didn't ask enough. This basically answers that question, what they told you to do. I'm always going to ask you an interpretive question. So let's add a question to this. Is there evidence a majority of sick bartenders got better. My English is not very good this morning. Is there evidence a majority of sick bartenders got better? Make sure you know you are never going to go back and discuss the sample proportion. The only thing you can discuss is the confidence interval. There always seems to be some confusion on the word majority. Majority means greater than 50%, greater than 0.5. So you're going to look here and ask yourself, is there evidence this is greater than 0.5? The answer is no. The entire CI is not greater than 0.5. That is the definition of majority. You will see that on some of my problems on handout 11. All right, you can pause me, and then we're going to go on to the second problem. This one's even longer. Most of it is actually not important, but pause the video, read the entire problem right there. All right, so again, another dated problem, but I'm here to tell you it's still a current topic. There are still teachers who need help integrating all the different new technologies that come out, because you got to remember, people my age, we did not even have the internet when we were growing up. And then also the all-inclusive classroom of how to meet the needs of all students at various levels. So we have 4,000 teachers. Well, we'll call this the teacher problem. So we have 4,000 teachers, and 21% said they needed extra help integrating technology. You can tell I changed something. Please do not round that to 20%. I want to make sure we get to practice the hard thing on the calculator. So please keep it at 19.99%. Said, oh, have I gotten this backwards? Sorry, I have. 21%, so let me read my problem again. Needed help with helping the disabled students. 19.99% needed help integrating technology. Okay, that's what the problem boils down to. I guess technically I've done it in backwards order. This is part B, this is part A, but it doesn't matter. You can see also in part B, I had to make another correction. If you are ever looking to compare two confidence intervals from two different populations, you have to have the same confidence level. This is not allowed to ask a 99 there and then a 95. You would not be allowed to compare those. So I changed it to 99. We're going to do 99% confidence intervals for each. Okay. So again, there are more than 4,000 teachers. These are the numbers for the 4,000 teachers. I'm trying to make a statement for all teachers, for the population of teachers. Let's set up each one, then we're going to go to the calculators together, because this is the one that students get tripped up on their calculator. All right, my p hat, got to just turn percent into a decimal, right? I'll come back to that z. Now I'm going to pick up my CI chart. I'm going to find 99% and I'm going to go all the way down to 2.58. Please do not let this confuse you. If you printed my notes, I have a 2.575. That's actually the more precise number, and I had that memorized. So you can ignore that. All you have to do is use the 2.58. All right, so that's the setup. Pick up your calculator. We're going to do this one first, the disabilities one. Go to Stat, Test, 1 prop Z int, hit enter. But here's the problem. This one is harder. It did not give me the information in fraction form. So, obviously the N is 4,000. That's easy. But how do I get the X? Well, you've got to figure out what 21% of 4,000 is. Some of you struggled with this on test 1. Of means multiply in mathematics. 0.21 times 4,000. You don't have to leave the screen. You can do it right here. I'm typing in 0.21 times 4,000. I'm going to hit enter, and an 840 comes up. Okay, so your calculator now tells you that's 840. The N is 4,000. Make sure you change it to 99%. Oops, N is 4,000. 99%. Calculate. Okay, that's the confidence interval for the true proportion of all teachers who need help integrating students of all abilities into the classroom. Now let's do technology. This one's even harder for the calculator. This is the one that 30% of you are going to get an error on your calculator if you do not practice this. So grab your 1 prop Z int. For that X, we're going to start by typing 0.1999 times 4,000. But then look at what happens when you do that. You get a 799.6. If you try to hit calculate right now, you will get a domain or dimension error. On these shortcuts on the calculator, it knows that X has to be a whole number. So you are going to scroll back up and you are going to round that properly, just how we always round numbers in mathematics. 799.6 goes to 800. So I'm just going back and oops, I need another 0. I'm just retyping 800 over top. The N is 4,000, sea level's 99, calculate. That is the confidence interval for the true proportion of teachers who need help integrating technology into the classroom. So that's technically the answers for part A and B. And part C just says, hey, we noticed from the sample that more teachers needed help with the disabled students. Does that hold for the population of teachers? We see that that's bigger for the 4,000 teachers, but they are asking a question about the population of teachers. So you're back to looking at these two confidence intervals. So basically the answer is no, because the confidence intervals overlap. Let me write that up here. No, you cannot tell, excuse me, you cannot tell which has a higher percent since the two confidence intervals overlap. All right, now we have just a few random notes that I want to give you that are very important. These are some just overall facts about confidence intervals. Confidence intervals in general. Doesn't matter which one we're talking about. As the sample size increases, the confidence interval width decreases. And that is actually a good thing. I want to approach this mathematically and intuitively. If I increase my sample size, that means I have a lot more information coming in. I'm feeling good about what I'm doing, right? Because I got a lot of different data. So since I'm feeling good, I'm going to feel comfortable making that confidence interval a little bit tighter. Mathematically, as n increases, look at both of your formulas for confidence intervals that we've done so far. You see how the n is in the denominator? If you put a bigger number into the denominator of a fraction, the entire quantity gets smaller. And so now we're just plussing and minusing a smaller number. So it's making it tighter. Let me make sure that everybody understands that 1/4 is smaller than 1/2, right? As we make the denominator bigger, the entire quantity gets smaller. Okay, so that's one truth. Now, in statistics, there is always what I call the seesaw effect. I got a good thing here. I got a tighter confidence interval. But guess what? That took me time and money to increase that sample size. So, there's always that sweet spot. All right, another truth. As you want me to be more and more confident, as the confidence level, 90, 95, 99, increases, your confidence interval width will increase, which is a bad thing. Let me give you an extreme example. I am 100% confident that the mean SAT score is somewhere between 400 and 1600. Well, I'm 100% confident, but that is a totally useless statement because what I tried to do was go from minimum to maximum SAT score. So you can get really confident, but have the results be totally useless. So that's intuitively how to understand that. But let's look at mathematical numbers. Let's just look at the z critical values here. Okay. Let's start at 90%. You would be using, for that z score, a 1.645. And if you want me to go up to 99%, I would be using a 2.58. 2.58 is a much larger number than 1.645. And where would that number even go into our formula? It goes right there. So at 99%, I would be plussing and minusing a much bigger number, which again, here's my confidence interval, it would make it wider. So I kind of already said it there, but let's make sure I state it clearly. Apples to apples here. All other things being equal, a wider confidence interval is a bad thing. Now, if you have all the time and money in the world, you can kind of see how you can manipulate and get whatever you want. Let's say I want high confidence. Okay, well, it just made my interval wider, which I didn't want. But then I could increase the sample size to bring it back down. So, but that takes time and money. So if you have all the time and money in the world, you could probably end up getting everything that you want. All right, we need this handout now. I don't know if there's a reason for me to rewrite this on the whiteboard. As election season really gets into gear in the fall, keep your eye out for all the political polls. And again, the good ones are going to state the margin of error at the bottom normally. And you're going to notice that most political polls always tend to have a margin of error of plus or minus 3%. Now, political polls are yes-no questions, so we are talking proportions. Remember, the margin of error is what comes after the plus or minus. I took, well, this sentence is very important. All political polls, the default is to have 95% confidence. That's how I knew to use a 1.96 there. I also happen to know that the good political polls are always use a sample size of about 1,000. Could be 987, could be 1,100, but approximately 1,000. So I ended up putting 1,000 in for the n. But this is the margin of error term. But how can it always just be 3% when we're going to have different sample proportions? So what I did here was just run through a few what-if scenarios. Let's just say that we do a political poll and 70% say that they're going to vote for some candidate, p-hat 0.7. Well, 0.7, 1 minus 0.7 would give you the 0.3. Calculate that out. Make sure you're okay with your calculator. You should end up with a 2.84% margin of error. Oh, that's close enough to 3. I don't mind that they're not showing the general American public 2 decimal places, right? They're not in stats class. All right, well, what about if it was a closer race? Let's say 60% said they were going to vote for a particular candidate. So I put in the 0.6, 1 minus 0.6. That one turns out to be almost exactly 3%. But what about if it's a really close race, like a 49-51% race? So 49%, 0.49, the opposite is 0.51. That turns out to be 3.1%. Again, I really don't mind that they're underestimating the error and calling it 3%. This is trying to give the general public the big idea about the margin of error. Now, you might say that I only tried 3 different p-hats, but basically, look, when I was testing the 0.7, I was actually testing the 0.3 also. When I was testing the 0.6, I was testing the 0.4 also. So basically, just those 3 examples, I have a range. I checked all the p-hats from 0.3 to 0.7, and it ranged from 2.84% to 3.1%. That is why that from most political polls, you will see a margin of error of 3%. I think one time I saw one at 4%, and that's because they had only done a sample size of 500, but that's pretty rare. Almost every single one you see will be 3%, and that is why. Just to kind of let you know where we are now in the videos and what's coming up. So first of all, you should now be able to do handout 11 numbers 5 through 7. Handout 12, all except number 3. A few of the ones on handout 12 are a little bit harder. So, as of right now, we are done with new material for test 3. But there will definitely be another whole video coming of just practicing problems, making sure you're okay with reading all these different problems and figuring out what to do with them. A lot of what I'll do will probably be from handout 12 because some of those are trickier, period. I've only done that twice in this video. I will probably do another video at some point once I open up maybe a discussion board for you guys to tell me which problems you're confused on, things like that. I want to try to get feedback from you guys over the next 2 to 3 weeks, obviously. So, you need to be practicing everything over and over. Make a list of the issues that you're having. Email me. Throw it into a discussion board once I get that up and running, etc. Hope to hear from you soon.